In section 5.5, we look at the real numbers and their properties. The union of the rational numbers and the irrational numbers is the set of real numbers. The sets that make up the real numbers are called subsets of the real numbers, meaning that all elements in each subset are also elements in the set of real numbers. So in the diagram below, you can see that the big square encompasses the rational numbers and the irrational numbers. And then the rational numbers purple square, we break it down into subsets. We have the integers, which encompasses the whole numbers, and the whole numbers encompasses the natural numbers. So you can see how they fit within each other using the diagram. The chart below lists each subset of the real numbers. So natural numbers are those counting numbers, 1, 2, 3, 4, 5, and so on. The whole numbers are the natural numbers, but we add 0 to the mix. The integers is the set of the whole numbers plus the negatives of those natural numbers. Rational numbers is the set of all numbers that can be expressed as a quotient of two integers with the denominator not 0, but these can also be expressed as terminating or repeating decimals. And the set of all irrational numbers is the set of all numbers whose decimal representations are neither terminating nor repeating. Irrational numbers cannot be expressed as a quotient of integers. So there's some examples to the right, but let's just go ahead and look at the set of numbers below. -7, -3/4, 0, 0.6 repeating, the square root of 5, pi, 7.3, and the square root of 81. Well, first things first, let's go ahead and simplify whatever we can. So the only thing that I can simplify in here is the square root of 81. So let's just go ahead and write what that actually is. The square root of 81 is 9. So now that everything is simplified, it will be easier to put it in the correct subsets. So let's start with the natural numbers. These are the counting numbers starting with 1. So the only number that falls into this category is the square root of 81. What about the whole numbers? Now, the only difference between the natural numbers and the whole numbers is that 0 is included in the whole numbers. So this means that from our set, we have the 0 and the square root of 81 that are both whole numbers. So you'll notice now when I go to the integers, I'm still using 0 and the square root of 81 because the whole numbers are a subset of the integers. So integers are the whole numbers plus the negatives of the natural numbers. So the only other number I can include in integers is that -7. We still have that 0 and we still have the square root of 81. Rational numbers are quotients or decimals that are repeating or terminating, plus all of the integers, the whole numbers, and the natural numbers. So we still want to include -7, 0, and the square root of 81, but now we can also add on -3/4, 0.6 repeating, and 7.3. So -7, -3/4, 0.6 and 0.6 repeating and 0, 7.3, and the square root of 81. And so either you're a rational number or you're an irrational number. So if it was included in the rational numbers, it cannot be included in the irrational numbers. So anything that's left over from the list needs to be included here. So that includes the square root of 5, which if you put it into your calculator, you'll see that the decimal just keeps going forever and ever, and pi. Pi is the most common irrational number we talk about. And what is a real number? Well, a real number is everything that is rational and irrational. So it's just the entire set. So -7, -3/4, 0, 0.6 repeating, the square root of 5, pi, 7.3, and the square root of 81. Now, what are the properties of the real numbers? When you use your calculator to add real numbers, you can enter them in either order. The fact that two real numbers can be added in either order is called the commutative property of addition. There are many other properties of the real numbers, and they are listed below. The closure property of addition just says that the sum of any two real numbers is going to give you a real number. The closure property of multiplication just says the property of any two real numbers is also a real number. The commutative property of addition and multiplication just says that you can change the order without affecting the operation. So commutative deals with the order. The associative property of addition or multiplication just says that when we change the grouping, it doesn't affect the sum. So if I add A and B or multiply A and B first and then add or multiply C, I could also do B and C first and then A. So associative just says that we can change the grouping without changing the sum or the product. The distributive property of multiplication over addition just says that we can distribute the multiplication to both parts or how many ever parts of the addition. The identity property of addition just says that if I add 0 to a number, then it's just the original number. The same idea goes for the identity property of multiplication, except instead of it being 0, we multiply by 1, because that's going to give me the original number. And the inverse property of addition and multiplication just says that when I add, I should get the identity. Same thing with multiplication. When I multiply these two numbers, I should get the identity, which was 1. So A plus negative A would give me 0, and A times 1 over A would give me 1. So we just want to name the property that is being illustrated. 3 times 7 equals 7 times 3. Well, this is just the order that's being changed here. So this is the commutative property. And this is of multiplication. What about the next one? 4 plus 7 being added first, and then we add 6, or adding 7 and 6 first, and then adding 4. So the only thing that changed here was the grouping. So this is the associative property. This time it's of addition. What about the third property? 2 times 3 plus the square root of 5 is equal to 6 plus 2 times the square root of 5. So if you notice, if I distribute the 2 to both pieces, 2 times 3 would give me the 6, and then 2 times the square root of 5 gives me 2 root 5. So this is the distributive property of multiplication over addition. What about the fourth one? Square root of 2 plus the square root of 3 plus the square root of 7, where we add root 3 and root 7 first. Or we have the square root of 2 plus the square root of 7 plus the square root of 3. So what is actually changing here? Is it the grouping or is it the order? Well, the grouping still has 7 and 3 together, so the grouping's not getting changed. But what happens is the order inside those flipped. It was 3 then 7, and now it's 7 then 3. So this is really a commutative property of addition. What about the next one? 17 plus negative 17 gives me 0. So we see that we got the identity of addition, which is 0. And the goal for that one talks about the inverses. Whenever we talk about inverses, the goal is to get to the identity. So this is the inverse property of addition. And the last one, the square root of 2 times 1 equals the square root of 2. So what we started with is what we ended with, which means we're talking about an identity, and the identity of multiplication is 1. Whenever we multiply a number by 1, we just get the same number. So this is the identity property of multiplication.